Unit Operation Classroom. This is the website. And today we are discussing recycle, part streams, single pass, and overall conversions. My name is Shekhar Bhattacharjee. For an irreversible reaction, let's say A to B, very simple one, containing inert in the feed. So the feed contains whatever the reactant, and it also includes an inert. Single pulse conversion, we'll see what is a single pulse conversion when it reacted at 70%. Which one of the following statements is correct? So before we look into the options, let us see what the system looks like. So let's say this is my reactor here, and here a feed coming in, assuming it is containing 80 mole percent A and 20 mole percent the inert. Now, this is just an assumption only to take a numerical example. So whatever the A coming in, out of that 70% would be converted. So 80 multiplied by 0 times 7, that means 56 moles of A would be converted. That means that's the amount of B that will be produced because it's just A to B. And the remaining would be 80 multiplied by 0.3, that's 24 moles of A would be remaining, and the inert, of course, whatever is here will just go as it is here, 20 moles, right? So here the overall conversion, we'll see more of that, is the same as the single pulse conversion, which is the moles of A reacted, which is 80 multiplied by 0.7, which is this one right here, divided by the moles in the feed, which is this one right here, that is equal to 70%. So in this case, overall conversion is the same as single pass conversion, and that is 70%. Okay, now let us see when there is a recycle, but there is no purge in the system. So let's say this is the same reactor here. And what we have, the feed is the same, coming in 100 moles of that, and that of course 80 moles of the reactant A and 20 moles of the inert that goes to the reactor. But now it mixes with the recycle. I'll show exactly what it is. So when it goes here, after that whatever is coming in, which is a mixture of this one and this one, so this is called the mixing point. 70% of that A, what is here, would be converted, and 30% of A would, of course, will not be converted, unreacted. So it will contain A, B, and I. And we are assuming there is a separator. This is an idealized separator where, of course, out of this A, B, and I, the entire amount of B will go here. This is an idealization. And the entire amount of A and I will go here. Okay. This is an ideal separator. And this A and I, of course, comes back and mixes here. So the inert, which is here, goes as it is, goes to here and goes here and goes here. And again, it mixes with more inert. So to give you a very quick example, what is happening here, if this is the amount of Fi, this is what is entering here after mixing with the fresh feed and the recycle. So in the very first case, pass one, where there is no recycle, very first beginning, so what happens? 80A plus 20I, which is coming, that will be here. Okay. And what will be here? Of course, out of 80A, 30% will remain unreacted and 70% will get converted into B. And of course, inert as it is will go here. Out of that, 56B will go directly here in the separator, and 24A and 20I will go right here. Okay. And that comes back and mixes again with this 80 moles of A and 20 moles of I, right? So if we look at the past two, you can see that fresh feed is coming as it is, 80 moles plus 20A, and this 24A plus 20I, which came as from the recycle here, this one and this one, which came as recycle, so that comes here. Okay, so the total would be that amount of A and I, so it has increased to 40. Out of that, again, the next time, that would be 30% will remain unreacted, 70% will get converted, which will, of course, go as a product. But again, this 31.2A and 40I, that will be recycled. So, as you can see, initially it was 20 in the feed. Now it has increased to 40. So, as you can see, the inert continuously starts building up in the system. So inert mole fraction quickly builds up and tends towards one, almost it becomes a totally inert. So the reactor fails. So this type of operation, when there is an inert in the feed, just recycling does not work. It needs a purge stream. We'll see how. In the next slide, we'll see what is the configuration of recycle with a purge stream. Here, as it is, the fresh feed comes in and mixes with the recycle as we have seen. It goes to the reactor, goes to the separator, which is the idealized one. That means A, B, and I. The entire amount of B goes here, and the A and unreacted A and I goes here. But here, instead of recycling the entire unreacted A and I, some amount is continuously purged in the system. So let's say there is a valve which is slightly open, and there's continuously and a stream goes out. So this is called purge. So let's say in this particular case, we are just assuming that there's 20% of this stream. Of this stream, 20% of is purged and 80% is recycled. Okay. So what is the idea of purge stream? To avoid buildup of inert, unwanted components in the reactor, so like byproducts, etc., so that at steady state, the total moles of inert in the feed, which is coming from here, that is continuously purged from here. So if I can design a system in such way that at steady state in a continuous process, whatever the amount of inert comes in, that will be purged, if we can design that way, but some amount, of course, will be recycled. But this amount, 20I, will be the same as what is purged. Then, of course, there will not be any buildup of the inert in the system, and the reactor will work nicely. So here, basically, what will happen that the 20 moles of inert which is coming in here, that must be equal to 20. What is the coming in here? 20% of that. These two should be exactly equal. So this must be equal to this. That means 20% of this we must go here. So if we do the inert balance, that is 20 moles of inert in the feed is equal to 0.20 of this one stream. So this SSI should be 100 mole. If we can set up like this, so it's 100 mole and 80 moles going in here, and of the inert, the that total 100 moles of inert will be coming in here. So out of this 80 moles of inert will go here, and 20 moles of inert will go here. Then of course this 20 moles and this 20 moles going out continuously. So this is a steady state system, and the reactor works beautifully. So that's the idea of the cycle with purge. We'll see little more details how the numbers work out. Let us take the same example here. Um, Here we have a feed, 100 moles of 80 moles of E and 20 moles of I. And here, let's see, after mixing, this is my Fi. So this is what is entering here. In this one, we have the moles of moles of A is AI, and the moles of I is II. I stands for here input, let's say. Okay, so here at this point, that means after mixing here, the amount of A is moles of A is AI, and I is equal to E naught is II. So if we take that, 70% of this one would be get converted. So A would be remaining 30% of this one right here, and the B would be 70% of this one right here, and the I, of course, will just go exactly like this. And this B, 70% of AI will go directly here, and 0.30 of AI will go right here, and the II as it is will go here. So that's what it is. Out of that, 20% of this stream goes right here, okay, and 80% goes here. So uh, if we do the A balance on this reactor, so let's say we do A balance on this reactor. AI, that means which is entering right here, that's the number of moles of component A which is entering here, input here, that should be equal to 80. That means what is this one plus what is coming over here, that would be equal to, see, this is 0.30 AI that is coming in, and that goes in right here and out here, and out of that 80% comes back as recycle. So this is my 80% as recycle, and this is 0.30 AI. So that's what it is coming right here and gets mixed up right here. So AI, what is entering here is 80 plus 0.80 to 0.30 AI, which is coming back from the recycle, right? So if we do that, this balance comes to 105.260. So that is basically 105.260 moles of A is coming in. If we do the I balance, what happens? This II, that is the moles of I inert that will be coming in here, that will be equal to 20, which is coming from here, okay? Plus, as you can see, this II, which is going right here, which just goes right here, and out of that, 80% comes in here, 20% is purged. So this would be equal to 0.80 into II. 0.80 stands for 80% and II, which is going right here. So II becomes 100 moles. Okay. So this becomes equal to 100 moles of inert. So if 100 moles of inert comes in here, so that 100 moles of inert goes right here, 80 moles coming in on here, and 20 moles of inert is continuously purged. So this is the 20 moles of inert coming in, and this 20 moles of inert continuously purged. Okay. So with that calculation and the total AI in number of moles of A here is 105.263 and inert is 100 moles. So this is the total here is 205.263. So if we do all the calculations, put the numbers here. So I have put in all the numbers right here. So these are the values. So this is 105.263, I is 100 moles. Of course, B is equal to 0 because the entire B is taken out. So here, if we do the calculation, A is 0.30 of AI, which is this value B, and C. So this B comes right here, and this A 100 moles and 31.5 goes right here. Out of that, 80% comes here and 20% goes here. Okay, so these are my calculations. Okay, now let's see, look at the option B. What was option B? First, let's look at option A. Recycle eliminates the need for per stream. Is this true? No, because if we recycle, we always need a person if it contains an inert, because so that otherwise there will be inert build up in the system. So recycle does not eliminate the need of per stream, which we have seen right here, where there is only inert. It continues, the inert starts building it. We need to have a per stream. So option A is not true. Recycle reduces the concentration of inert in the system. Let us see if that is true or not. So these are my calculations, what we have done here. So this is the final calculations, what we have done. So option B, let's see if this is true or not. Inert in the fresh feed is 20 mole percent, which we have seen here. This is the 20 mole percent inert coming in. Reactor inlet, which is right here, reactor inlet right here, is one inert. So here, as you can see, the concentration is inert concentration 100 divided by 205.260 added up, right? So 100 divided by 205.260 is 48.72 more percent. So here, the inert concentration is 48.72%. This is 20 more percent. This is 48.72%. Okay. And let's see what is the concentration in the recycle loop. In the recycle loop, of course, this is going to be equal to 80 moles coming in here. Out of this 100 moles, 20 moles went here and 80 moles went here. So this is 80 divided by 25.263. That is 76 mole percent. So as you can see that recycling does not reduce the concentration density. In fact, recycle does not reduce inert concentration, it increases. This is in the feed, so as you can see, it has increased at steady state. So this is the recycle inert concentration, and this is in the reactor feed. So recycling does not reduce the inert concentration. In fact, it increases. That's why the purging is necessary. So option B is also not true. So option B is also not true. Let's see, recycle increases overall conversion or not. Okay. Option C, we're looking into this one. What is a single pass conversion? 70%. What is the overall conversion? Let's look at it. Overall conversion is how much A has been converted. So 73.864 at steady state. So this is the amount of B. That means that's the amount of A converted. So at steady state, we just do like this. Okay. So here you can see that 73.864 mole percent of B has been converted, whereas 80 mole of A has been introduced as a fresh feed. So what is the conversion here? conversion is 73.864, which is the amount of B or the amount of A convert divided by 80, which is 92.1%. So option C is true. Recycle increases overall conversion system. And option D is recycle decreases overall. Of course, that's false because this is just the opposite of this one. Okay. So as you can see here, option A is not true. Option B is not true. Option C is true. Whereas option D is just the opposite of this one. So this is also false. So that is also not true. So decide this is the correct option. Okay. Now let us quickly look into some industrial application of this problem. In the ammonia synthesis, we know this is a reaction. Of course, this is not A to B, but still, you will get the idea. The feed is hydrogen from natural gas and, of course, nitrogen from air. So, argon and methane, comes as from the methanation reactor, which we have discussed in other problems, are the inerts to the reactor. So, purging is necessary to prevent this inert buildup in the loop. And the interesting, the single pass conversion is around 10 to 20%, whereas the overall conversion is 98%, and that is achieved by proper designing, intelligent designing of the reactor. That means recycling and the purging of the system. So recycle is essentially for economic yield. Now we'll see another example in the methanol production, which is this reaction here. We use syngas, which is the natural gas from natural gas deforming. So methane, nitrogen are inerts of the system. So there, what happened if we do not use the purging? So that dilutes the carbon monoxide hydrogen. So that's why purging is necessary. And this purge stream, of course, is sent to a fired heater for its calorific value right here. Okay, so single pass conversion is around 20 to 40%. Of course, depends on the catalyst, temperature, and pressure. Overall conversion is 97%. So again, recycle boosts overall conversion. So as you can see, this particular problem has a very wonderful and nice application in the process industry, and it is very necessary to clear this concept that the recycle does not eliminate the need for purge stream. Recycle does not reduce the concentration of the inert in the system. That's why purging is necessary. Recycle increases, if we properly design with a purge system, it increases overall conversion. Of course, when there is an inert, and recycle, of course, does not decrease overall conversion.